with today's class. So this is just for completeness. Well, with the kind of a new nice picture here of how the stereographic projection between the unit disk and the hyperboloid looks like. That of course I didn't draw it. It was Martin Freyer for Garion. Yeah, and then here are the formulas that I mentioned. I found a very nice video. So let me show it to you. So that's the Poincaré disk. And that's the stereographic projection to the hyperboloid. Well, of course, and now it zoomed out, so now it's kind of not everything very clear, but so I think it's a very nice animation. Right, so let me just okay. Reminder of what a Romanian isometry is, right? A Romanian isometry is a diffeomorphism that pretty much so that measuring an inner product is gives you the same result if you measure before sending, before going through the diffeomorphism, or after going through the diffeomorphism, right? And then at the level of tangent vectors, the way you go through the diffeomorphism is by applying the derivative. Right, then as I said, the exercise is that these are Riemannian isometries. Yeah, and now, okay, now the kind of the new stuff, right? So I have my, let's say that I have my Riemannian manifold. Just think of the hyperboloid, kind of for simplicity, and then if you think of the hyperboloid, then I take this one to be Minkowski's form. Yeah. So at each tangent vector, I have an inner product, Minkowski's inner product, and so I can measure the length of a tangent vector at any point of the hyperboloid. And then when I measure the definition, what would be the norm of the tangent vector? It would be the square root of the value of the inner product evaluated at v comma v. Right? Of course, if v is based at the point p, here I would have to say p. Right? So actually, yeah. So here I have to make a correction, because here it has to be g sub gamma of t. Yeah. Right. So the let's say the length of a vector which is tangent at p is defined as the square root of g sub p, the inner product of the tangent vector of the tangent plane or the tangent space at p, v comma v paired according to that inner product. Okay, so if I have a curve of class C1, and by class C1 what I mean is that it has first order derivative, and it's that the first order derivative is continuous. Or if it's easier for you to just think about curves of class C infinity, then just think about those. And then the G length, So you see G here is my Riemannian metric. The G length is the integral of measuring. You see this would become the norm of gamma prime of t, right, sub gamma t. Right? And somehow the idea, so I integrate this function with respect to t. So you see, for each t in the interval, this is a real number, right? So speaking about this integral makes perfect sense. It's a real, makes perfect sense because you see, class C1. Okay, now, what's the idea? The idea is that somehow, that somehow I have my curve, right? So let's say this is gamma of A, the point gamma of A, the point gamma of B, and somehow I have the curve, let's say, I don't know, I don't know, I'm always undecided what's the nicer picture. Yeah, and then what can I do? Well, for instance, I can approach it as we did in calculus of several variables, and then say, okay, the interval AB, you can partition it in finitely many segments, and those segments, you know, the kind of the points of the partition, you map them, and then you have their images, right? And something you can do is, okay, at the points of the partition, you can, and let's say okay, so these are also, yeah, and then at the points of the partition, let's say you go with the leftmost, let's say, and say, okay, so here take the derivative, here take the derivative, it could be its tangent, and it could be, I don't know, very long or very short, I don't know, depending on how the curve is parametrized, right? And so right, and then you can say, okay, and then measure this one, right? So it's kind of take its norm, take the corresponding norm of this vector, take the norm of this vector, take the norm of this vector, right? And then you see, but it's the kind of the norm according to the Riemannian metric. So in the hyperboloid, this would be really the length, the norm, kind of according to Minkowski's form. Right? Okay, and then you can say, as in calculus, this length can be approximated as as the norm of this tangent vector, right? So of gamma prime of t, in this case it would be like t0 for a general one for any of these points, it would be tj, right? And this norm is of course measured at the point gamma of tj, yeah, times the amount of time, right? The amount of time that this speed is applied, right? And that's an approximation of this distance, right? And so times, you see what in calculus maybe one writes like delta t. Okay, let's say just instead of delta, let's say t j plus 1 minus tj. Right? This is my like delta t, right? Or delta tj, or yeah, and then the whole distance then is approximated by just taking the sum of all of this. So this sum from j equal to 0 to, I don't know, n, let's say m, where m is the number of points in the of intervals in the partition. This sum somehow approximates the length of this curve. Okay, and then as I start refining the partition, this sum somehow really approximates, not approximates, attempts to this integral precisely. Right? So it makes sense to say, okay, so the value of this integral, I define it to be the length of the curve. But of course, the length of the curve according to my way of measuring lengths of vectors in the tangent planes. Right? Okay, and then, as I already mentioned, a shortest curve between 2 points is a curve that connects the 2 points, yeah, but also has minimal g length compared with any other curve joining them. Okay, so that's shortest curve, a shortest curve. Right? Exercise, a connected Riemannian manifold is always a metric space. So, sorry, I missed. I didn't explain this. Sorry. So let me maybe over here. Yeah. So what is the distance between 2 points? Well, is the infimum of the length of the curves that connect the 2 points. Notice just something, that I am not defining it as the length of a shortest curve, because it could be that a shortest curve doesn't exist, that a shortest curve joining them doesn't exist. That's perfectly possible. That's why I say infimum here. Of course, if there is a shortest curve, then that shortest curve realizes the infimum, of course. Now the exercise is that this definition of distance makes the Riemannian manifold a metric space. Again, if it's too abstract for you to think in terms of a general Riemannian manifold, then just think about the hyperboloid or the Poincaré disk. That suffices for me. Okay. And so now what I'm interested in is in finding some shortest curves in the hyperboloid. Yeah. And actually, these are my first candidates. Yeah. So take any point in the hyperboloid and any tangent vector, right? And somehow I think of this tangent vector as giving me kind of like an initial condition, right? I want to find a curve that passes through my point at time 0 with that velocity, with that speed. Kind of when I say with that speed or with that velocity, what I mean is that it has that derivative, right? That is, it passes with that direction and with that amount of with that rapidity, the rapidity dictated by that tangent vector. Yeah, and somehow I want the curve to be of constant rapidity, right? So that after passing there, of course, the direction may change, right? Because think of the hyperboloid. Of course, the direction has to change because I'm not in a plane. Right? The direction has to change, but I want that at least the rapidity doesn't. Right, and somehow my candidate to do that is this function. Yeah, so that at time t, you see this looks similar to this to just the usual kind of parametrization of the circle, right? Cosine sine looks similar, right? Except that of course it has to be modified and there has to be some hyperbolic stuff there. Oops, what happened? doesn't respond. Okay, if it's clear enough, then I just keep going. Yeah. Right. So you see, let's say, imagine for a moment that the length of the vector is 1, that is rapidity 1. So this becomes 1. So it's really, this would be hyperbolic cosine of t, and here I would have hyperbolic sine of t, and then divided by 1. Right? So this expression would simply be hyperbolic cosine of t times the vector p, the vector in three-dimensional space p, plus hyperbolic sine times the vector in three-dimensional space v. Okay, and if you think in those terms, this looks very similar to this cosine sine in the circle, right? But it's of course slightly different. And then if I really want to achieve any rapidity, then I'm going to have to I consider that formula. Yeah. Or if the vector is 0, right? So that I can't really perform this division. Well, if the vector is 0, then that means that I don't really want to move. Right? So I just stay at the point P. Okay, now exercise. This is really contained in M, in the hyperboloid. You see, in the end, it's really going to be the kind of the famous formula that something square minus something square is equal to 1. That's satisfied by the hyperbolic sine, cosine, and hyperbolic sine. Okay, and then the first lemma is that indeed at time 0 passes through P, and at least the rapidity is constant. Yeah, and that this I leave as an exercise. Yeah. So what's the exercise? Well, you have to take the derivative of this expression with respect to t, and then pair it with itself using Minkowski's form, and then take square root. And after you do all that, then there have to be like enough cancellations and so on so that this survives. That's the point. Okay, but so that doesn't mean that that alone doesn't mean that this is a shortest curve, right? Because, for instance, consider the circle, the unit circle, parameterized with the usual cosine and sine. I mean, the rapidity is constant, equal to 1, right? Equal to 1 because derivative of cosine is minus sine and derivative of sine is cosine. Yes, but between 2 points in the Euclidean plane, you see, between two points in the unit circle, it is not true that the shortest curve is that segment of the circle, right? Even though it has rapidity, constant rapidity. So having constant rapidity alone doesn't imply that it is a shortest curve. So we are not done yet. But we want, I mean, but that's going to be what happens, right? That you see, I mean, this is really defined for all real numbers. So it's really an infinite curve. But so that you see, whenever you take a finite segment, it's going to be a shortest curve between the extremes of the segment. Okay, right, and now that's the lemma. Well, not yet. The lemma is that if I take this special point, this special initial point, and this special initial tangent vector, then the corresponding curve for these special choices is a shortest curve. Okay. Now, notice this one is indeed in the tangent plane at this, right? Because it's, you see, I'm in the hyperboloid, and 0, 0, 1 is this point, and the tangent plane there is just the horizontal plane, right? So because there's a 0 here, indeed, this is in the tangent plane. at n. Okay. Yeah, so now, first of all, you see in this tangent plane, since I always have a 0 in the last coordinate, somehow in that tangent plane, really, it's really just kind of that tangent plane is actually kind of sort of Euclidean. The others are not, but that one is. Yeah, okay, now this norm is then equal to 1. The Minkowski norm, right? So here there's, yeah, it's equal to 1. So that means that this in this expression, this is 1, this is 1, this is n, which is 0, 0, 1, and this is 1, 0, 0. So you see the formula tells me gamma of t is hyperbolic sine of t in the first coordinate, and then 0, and then hyperbolic cosine of t in the third coordinate, because n is equal to 0, 0, 1, right? So that's what I have here. Yeah. So this here I just this just indicates restriction, right, to the interval. Okay. And then the hyperbolic length of the segment from 0 to t0 is just t0. Why? Because by this lemma, the rapidity of the curve is constant, and this is equal to 1. So the rapidity is always equal to 1, and that rapidity, I have that rapidity which is constant equal to 1, has to be integrated along the interval 0 t0. So it's really, so kind of this length really becomes integral of 1 from 0 to t0. So this is just t0. Okay, so I know that. So in this case it was easy. Right? So having constant rapidity makes computations easy. Right, and now I would like to show that any other curve going from n to sine of t naught 0 cosine, sorry, hyperbolic of t 0 or t naught, that any point going from n to the end point of this curve has length greater or equal than t naught, because I want to show that this is a shortest curve between its extremes. Okay, so I take any curve of class C1 connecting n to the end point, of the curve, right, which is this point, right? I mean, and here I'm writing eta as a kind of as a triple of functions, right? As an ordered triple of functions. So eta 1 is the function that gives me the first coordinate, eta 2 is the function that gives me the second coordinate, and eta 3 is the function that gives me the third coordinate of eta. Okay, and now I use the fact that I know that phi, the stereographic projection from M to D, is a Riemannian isometry. Because since it's a Riemannian isometry, let me go back to the definition of length. The definition of length is given as, you see, you have to integrate the square root of this inner product. But somehow, if you have a Riemannian isometry, you can replace this inner product with the inner product under the image, right? Because in a Riemannian isometry you have this equality. So the inner product you can compute here, or you can compute here in the image, right? You can take the inner product, but in the image. And the value doesn't change. And so that means that the hyperbolic length, that means that the length of the curve is the same in the domain, or that the length of this curve is equal to the length of its image under the Riemannian isometry. Yeah, which is what I'm saying here, right? The length of my curve eta, that is a curve in the hyperboloid, is equal to the length of its image under phi, right? So what's its image under phi? I mean, so notice, so it's a curve in the hyperboloid. So I don't know, it's some curve there. And from the hyperboloid, I can map to the disk, which is somehow sitting horizontally there. Let me write it in blue. Yeah, and then this curve, I can just follow it by phi, and then I have some curve here, right? But so that's why I have to write eta followed by phi, right? And eta followed by phi would be this one. Okay, and now in terms of these three entries, what's this? So I go back to the formulas, and you see phi of an order triple, it has to be x plus yi, and then divided by this one plus 1. So that's why I write here. Right? I mean, this one plus this one I divided by this one plus 1. Right? But as functions. Right? So I mean, so this is really a function that goes from 0 t0 to the disk. Right? Yeah, and then this is equal to this. Okay. Now, of course, here I forgot to write 2. I think it's 2 here. Yeah, and so of course I have this inequality, right? So that's obvious. Yeah, so that means that what does that mean? So I can like just divide by whatever positive. So I divide by 1 plus eta 3 square, both sides, right? And then the inequality is preserved. Okay, so the inequality is preserved, and then I can multiply by -1, and then the inequality is reversed, and then I can add 1, and then this inequality here is preserved. So because of this, I also have this. Yeah. Okay, and now once more, you see these are positive numbers, because I mean, why is this positive? Why is this positive? It's because this lies on the disk, right? I mean, if you take the norm of this square, it's precisely this. So this is always positive. And so, since I'm speaking about positive numbers, when I take their inverses, this inequality is reversed. Right? And then I multiply by 4, and then I obtain this inequality. Okay. And here, oops, I mean here, I don't know why I made this mistake. And here also, here there should be nothing here, right? Because here is eta 1 square is by itself. So maybe let me fix it. Okay. Right. So I have this inequality, and so now, well, okay. So I still have some way to go. And so now what I'm going to do is I'm going to take the derivative of this. Recall that this is a function from 0 t0 to the disk. Right? This is the function phi preceded by eta. And so I'm going to take the derivative of this as a function that, from let's say from R to R2. Right? Yeah. Yes, you are completely right. Yeah. I'm sorry. Yeah. Right. I mean that. Yeah. Yes. You are completely right. The one defined in 0 to 0 is this other one. It's this other curve. Yes. Okay. And so now I take its derivative as a function. You see, as a kind of as an R2 valued function of one variable. And its derivative is, well, coordinate by coordinate, right? So first coordinate, second coordinate. Yeah. And take that derivative, and I take the norm, and of course but now the hyperbolic norm. So for the inner product that I introduced for the unit for the Poincaré disk, and of course based at the corresponding point, right? So here really is kind of just to really keep track of the point where I'm taking where I'm measuring. Right? That's it. So kind of this shouldn't confuse you too much. Right? It's kind of just, in a way, it's kind of just a reality check. Okay. Yeah. Okay. So this norm is then you see, you see, how do I say it? I have to take, so for this norm, I have to take the Euclidean inner product of just this vector. Let's say this comma, sorry, this comma this, the Euclidean dot product with itself, times this guy. Right? If you remember the formula, so I can revisit that formula if you want. Just so that it's not confusing. Yeah. So you see here in the Poincaré disk, the inner product of two vectors is the usual Euclidean inner product times 4 times something squared, right? And then when I take square root for the length, this square goes away, right? And so so what I obtain is just this 2. It should be 2 without this, right? Yeah. So I go back to the other one. And so I have to do that here. And so that's why I did this computation. But there should be a 2 here instead of a 4. Well, okay, it's still true. And you see, when I take this one, so it's kind of here with the 2 is the factor I have to multiply with what? Just the square root of this square plus this square. Right? Okay. Right, but that's greater or equal than square root of only one entry square times this, which is also less or equal than that. Right? So here, what I'm saying is this one is a product of two things. This one is a product of two things, and the point is that the first factor in the product here is less or equal than the first factor in the product here, and the second factor in the product here is also less or equal than the second factor here. So that's why I have this inequality. Okay. Okay, and so you see this function, this which is what I have to integrate for the length of this one, is greater or equal than this other thing that I would have to integrate, but now for this curve that has imaginary part equal to 0. Yeah, is it clear what I'm saying? Yes. So this length, the length of this one, is greater or equal than the length of just this curve without the imaginary part. Okay. Now, okay, so there's still some way to go. Okay, but now let me write nu equal to this, what is inside here, because then you see the length of this one is I have to integrate. So you see this is nu, and so what do I have to integrate? I have to integrate for this length. I have to integrate the square root of nu prime of t square. So let me write it a bit more clearly. Square root of nu prime of t square times 2 divided by 1 minus nu of t square. Right? That's kind of what I just said when I went into this part. Right? And then that's what I have to integrate for this. Right? And then if you think about it, that's precisely what is written here. Right? Because square root of a square is just the absolute value of the thing inside. Right? So absolute value, and that's just the absolute value of a real number. And then this 2 is this 2, and then here I have precisely this. So I have to integrate from 0 to 1, right? As Jonas, right? As Jonas said, from 0 to 1. Right? Yeah. So, okay. Now, yeah, and then integrating absolute value is you see, absolute value is always greater or equal than non-taking absolute value. So I have this inequality of integrals. Right, and then here I realize that I can make a change of variable, right? Because I have some function of nu, and then here nu prime, right? So it's a change of variable, and so nu prime disappears, and I have d of nu, and then it's just the function, right? So this 2 goes outside, and I take the function of nu, right? And then I don't know, I check my table of integrals, and then I realize this, right? Okay. Ooh, okay. Now I'm halfway, but now exercise for any point here in the closed open interval. I have this formula, right? Hyperbolic sine of 2 times hyperbolic tangent arc of r is this expression exercise. Okay, that I'm about to use, because you see that's here I have precisely something like that. Okay. Now, of course, I have this square minus this square equal to minus 1. Which comes from where does this come from? It comes from the fact, you see here it's only with etas, right? It's only with etas. So what I have is let me think. Because what I have is eta 1 square plus eta 2 square minus eta 3 square equal to minus 1. Sorry. Yes, but evaluated at 1. Evaluated at 1 is eta evaluated at 1 is precisely this point. Right? That's what we said. Eta of 0 is n, and eta of 1 is this, which is this point. Yeah? And so for when I evaluate it at 1, it becomes this one square minus this one square, and it's equal to minus 1 because it sits in the hyperboloid. So I have this equal to minus 1, but I'm going to use that a couple of times now, because you see this one is by the exercise equal to this one, where I plug in nu of 1 instead of r. Okay, so I plug in nu of 1 instead of r. And now I remember what is nu, right? Nu is this, so, and evaluated at 1, right? So this goes here. Yeah, okay. And then you see I just perform the computation, right? So you see I force a common denominator, right? And then perform the division, right? I mean, it's a quotient of two quotients. I just perform the operation, and I arrived at this. So you see this really comes from having this here. So kind of from forcing the denominator. Okay, now here, what do I get? So for instance, here in the denominator, I have 1 plus 2 times eta 3 of 1 plus eta 3 of 1 square minus eta 1 of 1 square. So I use this one, right? So kind of the eta 3 square minus eta 1 square becomes 1. Yeah. Okay, and that 1 plus this other one is 2. Right? And then this other 2 comes from, you see, it's because in this square I have 2 times this. Okay. Now in the numerator, I just develop the whole square, so it's here. Okay, and now this one I substituted with using this identity, right? I mean, it's kind of, yeah. So I replace this 1 with using this identity, right? So it's here, and then the rest is equal. And the point of doing that is that I also get this one cancelled. Yeah, and then this one with a 2. Yeah, okay, so it becomes this, and then what? Right, and then here you see you see here I can take eta 3 of 1 as a common factor, and then I get a cancellation, and then the common factor survives. Right? I mean, when I take eta 3 as a common factor, I obtain eta 3 of 1 as the common factor times precisely this. So that, yeah. But eta 3 of 1 was what? Eta 3 of 1 was hyperbolic cosine of t0. Right? So I arrive at the following. Hyperbolic cosine of this guy is equal to hyperbolic cosine of t0. Now, this is a positive number, well, it's a non-negative number, and t0 is also a non-negative number. And hyperbolic cosine, if you restrict your attention only to non-negative real numbers, it's injective there. If you look at the graph of hyperbolic cosine, it looks something like this. It looks something like, let's see. I don't want to make a silly mistake, but I don't quite recall at which height, but it looks like this. But if you restrict your attention to just the positives, it's injective. So if you have 2 positive real numbers that give you the same value of hyperbolic cosine, it's because they were equal already. And so what I obtain is that this 2 times hyperbolic arctangent of nu1 is equal to t0. Whew, okay. So you see this hyperbolic length in the hyperboloid, recall that eta was in the hyperboloid, is equal to the hyperbolic length of just mapping to the Poincaré disk, because going to the Poincaré disk is a Riemannian isometry, this we already said. The explicit expression of this curve in the Poincaré disk is this one, as we said. That was greater or equal than the length of just the real part, right? That we excluded. We said, okay, we can delete this and then obtain this inequality. Okay, and this was greater or equal. So let me see. This length is greater or equal than this two times hyperbolic arctangent. Okay, but this number, as we said, has to be equal to T naught, because they are non-negative real numbers that give me the same value of hyperbolic cosine. Okay, it's T naught, but T naught, fortunately, was precisely the length of the curve I was interested in. So, the length of my arbitrary curve in the hyperboloid that joins the two extremes of this curve is greater or equal than the length of the curve of my candidate curve. So after all, my candidate curve is a shortest curve between the extremes. Right? Okay. Now notice the following. Okay, so okay, it was kind of some work, but we did it. And now I want you to notice this. This here is the correspondence rule for my curve, and you see it really is. You see, in y is equal to 0, so I'm really kind of sitting only in the xz plane, and in the xz plane, well, it's precisely a hyperbola, right? I mean, the xz plane was a hyperbola, and this is just traversing that hyperbola, but using the hyperbolic functions. So what I'm saying is traversing the hyperbola using the hyperbolic parametrizing that hyperbola with the hyperbolic cosine and sine. That is precisely well, that hyperbola is a shortest curve. When now I see in the whole hyperboloid, but not only that, it gives me constant rapidity equal to 1. So it's actually that hyperbola is the shortest curve in between any of its points. When I consider the whole hyperboloid, that is kind of leaving the xz plane already at some length to the curve, right? Okay, but not only that. It's parameterized by arc length. So the hyperbolic functions cosine and sine give me the parametrization by arc length. Is it clear? Yes. Now notice here. We usually want things. For instance, in the case of the circle, cosine and then sine. And then in the case of the hyperbola, it's also hyperbolic cosine and then hyperbolic sine. But the point is that here my hyperbola is really rotated. That is why the sine appears first and the cosine appears later. Okay. But what I want to convince you of is that this is really just a kind of an old friend. It's kind of just the hyperbola parameterized with the hyperbolic functions. And what I want you to notice, that's the correct parametrization if we think in hyperbolic terms, in the terms of hyperbolic geometry. Okay, so now that was one shortest curve, right? But I would like to to compute some more. Yeah? So well, not to compute some, well, yeah, kind of to prove that my other candidates are always shortest curves, right? So that in general, this always gives me a shortest curve. And that's what the theorem says. Right? That if you take any of those candidates and kind of just take a finite segment, oh, well, here should be everything. Okay, so let me try to fix it. Oops. No, okay, so it wasn't so easy. Okay, anyway, so my point is that it should be a subindex. Yeah. Okay, anyway. Right, so when I take any of my candidates and I just take a finite segment, recall that my candidate really is a curve defined on the whole real numbers. It's an infinite curve on both directions. So when I take just a finite segment, it is a shortest curve between the extremes. Okay, now the point is that now I have a lot, I already have a lot of tools at hand, because I know now that the orthochronous Lorentz group and the restricted Lorentz group are Riemannian isometries. Hence, preserve lengths of tangent vectors, and hence when I integrate, the value of the integral doesn't change. In other words, what I'm saying is a Riemannian isometry always preserves the length of a curve. We know that now, and now it really follows from a series of exercises. So the first exercise that I think is really nice is that if you take the curve that we just work with, this special curve that starts at the north pole with this initial tangent vector, the tangent vector 1, 0, 0. So the one that we studied here. The one that we studied here. Well, okay, if you take that curve and you multiply it with a matrix in the restricted Lorentz group, well, that gives you precisely the curve, the kind of the candidate curve that starts at A times n, at the image of n on that element, with this initial tangent vector. Okay, this is the exercise. It's not hard, and I would say it's a very beautiful exercise. Right. First, second, the stabilizer at the north pole acts transitively on the unit circle, and actually I would say this stabilizer is isomorphic to the unit circle, right? And my point is, it acts transitively on the unit circle, in this tangent plane. Okay, so this is a tangent plane. I have an inner product on this tangent plane, which is Minkowski's inner product. So in that plane, I have the right to speak of a circle in that plane. Okay, so I speak about the unit circle there. Yeah. And you see, if I take a Riemannian isometry, I mean, if I take an element of the restricted Lorentz group, and that element fixes the point, well, in particular, it sends this tangent plane to itself, and it preserves lengths of vectors. So it takes the circle to itself. This unit circle contained in this tangent plane is preserved by any element here, because any element here preserves the inner product, Minkowski's inner product, preserves the value of Minkowski's inner product. So preserves the length of any vector here. Right? And notice this, since it leaves n fixed, it takes this tangent plane to itself. Okay, and then the exercise is that the action of this guy on that unit circle is transitive. Okay. Right. As you can see, part of the exercise, and I would say most of the exercise, is just get used to thinking into this kind of differential geometry terms. Right? That they have a tangent plane, and then my Riemannian isometry, or my diffeomorphism, takes that plane to some tangent plane, but this means that the tangent plane goes to itself, and then being a Riemannian isometry means that in particular that the lengths are preserved, so the unit circle is preserved, this unit circle is preserved, and so on, right? I mean, kind of, I would say, once you get used to thinking in this differential geometry language, the exercise actually is very easy. Okay. All right, and now the final exercise here is, if you give me 2 points in the hyperboloid, and you give me 2 tangent vectors that have the same norm, the same Minkowski norm, right? And both are tangent. You see, I have my 2 points. So if you want, let me draw quickly. So I have my I have the hyperboloid, and I have my 2 points. Let's say P1 and P2, and I have a tangent vector here and a tangent vector here. Yeah, so those are V1 and V2. But and then such that you see the norm of this one is equal to the norm of this one. Yeah. Okay. Okay. In that case, there is an element of the restricted Lorentz group that takes this point to this point, and its derivative sends this vector to this vector. That's the exercise. We already know that there is that if I don't care about tangent vectors here, if I don't care about this, I already know that the action of this one on M is transitive. So I already know that there is at least something that sends this to this. Now that one sends this vector to some vector that may fail to be V2, but has the same length as the original one, hence the same length as V2. Right. Okay, and now you see I can move through this, I can move along this circle in this tangent plane, but I can move using an element of this one because of the previous exercise. That's the point. So the details, I leave them to you. Right, and then the theorem follows, because you see, because I can go from the pair n comma e, so n comma e1, which would be like my point, would be one of these points, let's say n comma e1. From there, I can go to any other point, p2, and with any unit tangent vector, right? Using I can map this pair to any point p2 with any unit tangent vector, right? And when I do that, and I apply A to the curve, I obtain precisely the corresponding candidate curve. Okay, but you see, so that means that any of my candidate curves can be seen, well, of course, with a unit vector, So right now I'm arguing only with where the vector chosen is unit, has norm 1. Okay, but that candidate curve is A of the curve I already studied. And applying A preserves the length. And applying A to this curve preserves the length, and applying A to any other curve preserves the length of this any other curve, which was already greater than the length of this one. So at least when my vector is chosen with norm 1, this is indeed a shortest curve. Okay, but if the vector is any other vector, you see, it's just a reparametrization. It's just, you see, if I have, let's say, a vector of length 2, well, rapidity is 2 always. So that means I'm really traversing the same curve, but with twice as fast. But it's still the shortest curve. So the theorem follows. Yeah. Okay, so good. So now, right, okay. Yeah, okay, so let me go with the order I have here. Okay, for any 2 points, there is a shortest curve connecting them. Right? I mean, so right now, notice I have a family. I have my candidate curves that I already showed are shortest curves. And but I still haven't established that with these curves I really can go from any point to any point. I haven't. I mean, what if what if I only defined a very small family of curves, and then I haven't found? It may be right now. It may be that there could be a pair of points that are kind of not joined by my candidate curves. Okay, but so I still have to prove this theorem. That's my point. Now, given any 2 points, there is a shortest curve connecting them, and now the argument is more or less simple. I have my 2 points, and I can use an element of the restricted Lorentz group to place one of the 2 points in the North Pole. Okay, I place it in the North Pole, and then I use a rotation around the z-axis to move it to the xz plane. Okay, and in the xz plane I already found a shortest curve. Okay, and then I map back. So that's the argument. So part of the argument is that when I take rotations around the z-axis, those rotations around the z-axis really belong to the restricted Lorentz group. But this was an exercise that I left last time. Okay, so for any 2 points, there is a shortest curve connecting them, right? And then here is some picture of some shortest curves. Okay, it's kind of course, it has more information than just that. Right? I mean, this I didn't do it myself, right? So I took it from here. So these are some shortest curves. Well, the ones you are seeing. But it has more information, right? So somehow it's also seeing their images on the stereographic projection in the Poincaré disk, right? So so this would be somehow like my curves. For instance, this is the curve this is the curve phi preceded by eta that we saw. This is precisely that curve, because you see it's xz plane. Well, actually, that's okay, depending on how you think, whether it's the x-axis or the y-axis, but projected, right? So this is precisely the curve eta, and somehow this is precisely the curve. Sorry, this is the curve phi preceded by eta, and this is precisely the curve eta that we saw, that hyperbola. Right, and then there's some more information that we haven't proved, that these seem to be segments of circles, and these seem to be orthogonal here. So that's going to be a theorem at some point, hopefully very soon. Right, so I'm running out of time today, so I think I want to, yeah, so yeah, okay, so yeah, so let me keep going. I mean, I have a couple of videos that I want to show you. Now I'm undecided whether now or on Monday. But no, let me go with with a theorem, which I think it's also really beautiful. I mean, this I think it's a very beautiful formula, and it's, you see, it really practically computes explicitly the hyperbolic distance between 2 points in the hyperboloid. It practically computes it just in terms of the Minkowski's form, and it practically tells you that it's pretty much equal to, you know, up to some sign to the Minkowski's form, and up to, okay, taking cosine, hyperbolic cosine. Right? So I mean, this distance is really the hyperbolic arc cosine of this one, right? And this is just Minkowski's form of the 2 points. I mean, I would say it's really spectacular. Okay, now, of course, if the 2 points are equal, this is just obvious. So let's suppose they are different. And then, as I said, I can my 2 points, I can send them to, one of them to the North Pole and the other one to the kind of to the wall xz. How? Well, first I move one of them to the North Pole and then I perform some rotation. Okay. And actually here, right? It's kind of on the correct side of the xz wall. All right, and then we said that T naught was precisely the length of the shortest curve from n to this point. That is this distance, right? So T naught is this distance, okay? But this distance is equal to the distance between P and Q, because A preserves those distances, right? Because it's in the restricted Lorentz group. Okay, so T naught really is this distance. Okay. On the other hand, you see cosine of T naught. Well, notice if you pair n with this point, recall that n is 0, 0, 1. If you pair n with this point, you really obtain only minus hyperbolic cosine of T0. Okay, so cosine of T0, hyperbolic cosine of T0 is minus the pairing, right? Okay, but A inverse preserves the pairing, or if you want from here to here, A preserves the pairing. So this pairing is equal to the pairing of P with Q. Okay, so hyperbolic cosine of the distance is equal to minus the pairing. So that's precisely what is written here. Okay. Okay, so this is really great. We can compute distances in the hyperbolic in the hyperboloid. Yeah, and then maybe let me state this theorem without proof today and show you the two videos. So if I take any shortest curve, here when I say the image of the shortest curve is kind of, recall that a curve is really a function from some interval to the hyperboloid, right? So really what I really see as the curve is really just the image of the function. That's what I mean here. Anyway, when I take a shortest curve, that shortest curve is actually contained in the intersection of M with a plane through the origin. So in other words, shortest curves in the hyperboloid, they are not like arbitrary, they are not chaotic, they are not crazy. They are really kind of, they really see, they still have Euclidean control of them, because they are contained in the intersection of some plane that passes through the origin with the hyperboloid. So it's not like they look crazy over there. Okay. Okay. So now I ran out of time, so I'm not going to go through the proof today, but let me show a couple of examples. Well, a couple of videos. Yeah. So, and then you can see the point moving there, right? And then what you can see there is, well, this plane that I just mentioned through the origin. Also see the projection to the Poincaré disk. And now something that one should not get confused about is, you see, the plane. The plane is not, that plane that you are seeing there is not the one from the stereographic projection. The stereographic projection is not from the origin, it's from 0, 0, minus 1. Another one, another video. Okay, so you see that the kind of the plane is really moving, and what you are seeing is the corresponding intersection. So that's also how the shortest curves in the hyperboloid look like. Okay, so